How's it going, Jacob?
You good?
That's cool. Feel free to ask me any questions while we're waiting. We got some people coming, but they're only about a minute before class starts. So I don't remember being this bald last time I was here. Good Lord. That is a bald head. Of course, I shaved it, so that didn't help. Hannah, Jacob, Jennifer, feel free to ask me any questions you might have before we get started. Oh, got more people coming. Woohoo! Way up. All right. Well, it's past time, so I guess I should go ahead and get started. I want to go ahead and finish up. I mean, I did chapter 8, and to be honest with you, that's really that one problem I worked through with that one equation. It's pretty much uh, just about all you need to know and you could probably get the rest basically from the book. That being said, I still feel kind of bad, so I want to go over some of the examples in the book, and I'll go over them using my version of conservation of energy. Plus, I also got to introduce you to what I really did say, which was part of that mathematical diversion I took, where I told you that, if one of these facts is true, all of them is true. And the first one is that the forces you're dealing with, the force is conservative. That was number one. Number two was del cross F was identically zero, and that means it's not zero for a specific value of x, y, z, but it's zero period for all. So you actually have to calculate that cross product where it's a determinant of a matrix. The determinant of the matrix is, well, the matrix is made such that the first row is I hat, j hat, k hat. The second row is derivative with respect to x, then the derivative with respect to y, and then the derivative with respect to z. They're actually technically partial derivatives. And then the third row is the x component of f, the y component of f, and the z component of f. And if you calculate that and it turns out to be exactly zero, no matter what particular x, y, or z you use, then that is the definition of a curlless field. And that's also another definition of a conservative field. So, like I said, if the force is conservative, then two, the curl of f is zero, and then three, the integral of along a path from A to B is independent of the path. In other words, if you calculate the integral from A to B of f dot dl along a path, then it's going to be some special function u of b minus u of a that doesn't depend on the path whatsoever. That's another line. That's the third part. That would be true if one of those are true. The fourth part is any closed integral. So an integral that starts in one point and can do all sorts of stuff, as long as it ends up in the exact same point at the end, then that integral will be, or that path integral will be zero. That's the fourth condition. And the fifth condition is there exists a scalar field u of x or u of x, y, z such that f, the force, is equal to the negative gradient of v. So that's the last bitty part that I wanted to make sure I showed you and gave you an example of. So feel free to ask me any questions. I'm going to go ahead and share my page and start on with some predecessor conservation of energy stuff. So these examples will largely look like the ones in your book. That's the main thing, is just so you'd have some familiarity with those types of problems and then how I deal with them. So this is chapter 8 continued. And if I have the time, which I should be able to go into the beginnings of chapter 9 and at least get you some of the initial credible facts so you can get started working on that. And then next time I'll come back and do a lot of examples, but hopefully that'll help. So the first problem I'm working here is we're going to imagine a roller coaster. The roller coaster has a 1,000 point. Okay, so in other words, it's basically, I'm saying it's 1,000 kilograms is the mass. but the mass is in fact carried out to 4 sig fig. So I'll put a dot next to the kilogram just to let everybody know. Again, in your textbook, your author would call that ambiguous if it says 1,000. In the way I teach in my labs, if there's a decimal point on it, then it's not ambiguous. So that's why I did that. What we see here is the roller coaster goes level at a height of 15 meters below above the lowest point on this part of the roller coaster, and then it goes up an additional 10 meters, and then there's a downward track, and that downward track goes all the way down to the bottom. And what we're trying to do with this is to express to you that the potential energy really can be can't have an arbitrary constant added to it without any damage being done. And you can see that partly from that number 5 step that I was telling you. There exists a scalar potential U of X, Y, Z such that F, the force, which is often the thing that you can measure, is equal to the negative gradient of U. That gradient is something that is a derivative, basically. So if you had a constant added to it, the constant would disappear. You can also see that ultimately the difference in potential is what matters. So when you change potential energies from one spot to another, it's the potential energy final minus potential energy initial. If both of them had a plus C added to it, those would cancel out. So hopefully you'll see that now. So let's start off. I've got the diagram drawn here, and I've got the actual words written off to the right. It says for part A, they want us to calculate the potential energy at B, so that's U sub B, and also the potential energy at C, but they want me to do so relative to A. Okay, so and what I mean by that when we say relative to A is we're going to go on the assumption that A has y equals 0. So for part A, y equals 0 at A. That means U of B is equal to, as always, mgy, but that's going to be 1,000 dot, there's the dot I told you about to make sure we can have 4 sig figs, times 9.80 meters per second every second. Remember, that's also meters per second squared, but I like to say it as meters per second. And then the height of location B above A is just 10 meters. So this is going to be 10.0 meters here, and therefore we get 98,000 times 10 to the third joules. That is the potential energy at B, and I'll say relative, to A. Okay, now I can do UC the same way. UC is going to be mgy, which equals 1,000 kilograms times 9.80 meters per second every second, times this time, notice since I called the 0 the height of A, now I've got to go down 15, so that's going to be negative 15.0 meters. And of course, this is basically the same thing plus another half of this. So half of this would be 49. So this would be 147 times 10 to the third joules, again, relative to A. Okay. So we can now do part B. And for part B, they want to know delta U going from B to C, which of course is U at, it's supposed to be U at C minus u at b. Remember, it's always final minus initial. So from this, we can see that this would be, oh, by the way, I forgot a negative sign over here. Don't forget that, everybody. See the negative sign by the 147? That has to be there. So I'm now going to say negative 147 times 10 to the third joules minus UB. And UB is 98.0 times 10 to the third joules. So we get negative 147 minus 98. That's negative 245 times 10 to the third joules. Now, technically speaking, the way that worked out is we had 3 sig figs at the top. We had 3 sig figs on the second line as well. Oh yeah, I guess it does have to round off to the nearest whole number. So okay, whole number past the mantissa, that is. So those are our actual answers. Anybody have any questions for that? I'm going to circle this too. And then this is delta U. So I'll circle this as well. No questions on that? Pretty straightforward, hopefully. All right, let me put up my chat window. I keep forgetting to do that when I do this. It's okay. Just in case anybody asks. Now we're going to do part C. And part C is just asking us to do the same thing, but this time I'm going to take it relative to C. So what I'm going to say is UB is equal to 1,000 kilograms times 9.80 meters per second every second. And then the height of B relative to C in this case is actually 25. So I'm going to say that's 25.0 meters. And this gives me 245 times 10 to the third joules. Okay. Basically, I just realized that 10 plus 15 is the same thing as 25. So all I really had to do was add the 98 and the 147, which I just finished doing. So that's why I knew it was 245 times 10 to the third. Okay. Now I'm going to take UC, which is 1,000 kilograms times 9.80 meters per second. And then this time the height of C relative to C is 0.0 meters. So this gives me 0. And then that gives me, of course, delta U, which equals UC minus UB is equal to 0 minus 245 times 10 to the third joules, which equals negative 245 times 10 to the third joules. And we can see that that is, in fact, delta U exactly the same that we got last time. And that's the main point of this whole exercise, is just, again, showing you that changing the origin of coordinates is really not a big deal. Do the same thing here. I'm going to say this one's equal to UB. And that's relative to C. And relative to C. And relative to C. Anybody have any questions on that? I know that could have been done a lot worse, but not much. All right. So this one is relative to C. This one's relative to C. And this one's relative to C. Shawnee, I think somebody's knocking on the door, baby. All right. Any questions on that? All right. Looks like y'all are getting it. I don't see your faces this time, but that's okay. All right. Let's go again. Now, here's where I get to show you how you can get the actual force from a given scalar potential. I've actually taken some liberties and actually changed this up quite a bit from the version of the textbook had for an example like this. And what I'm going to remind you of is the fact that the force F is equal to the negative gradient of the scalar potential. Sorry about the dog, everybody. So the force F is equal to the negative of the gradient of the scalar potential U of X, Y, Z. And I'll remind you guys that the gradient is a vector operator. So I can put like a little underline here just to remind you, hey, this del is supposed to be, and that's another word for it, del, nabla, whatever. Anyways, that is supposed to be put to the left of something. And then that something is the thing that's being operated on. And it's defined in terms of the partial derivatives. There's a partial derivative with respect to x. Again, there you leave a space to the right of that. J hat partial with respect to y. Again, leave a space to the right of that. Plus k hat partial with respect to z. Now, if you wanted to do this in coordinates other than Cartesians, there's a whole different branch of mathematics where you got to relate this gradient to the gradient in that new coordinate system. So it's a lot of work. I can also put these under bars over here just to remind you that it goes that way. You can let this operate directly on a scalar, which is what I'm getting ready to show you. I can let that del operate on a dot product. So I could put a dot there with a vector after it, or I could put a curl, which a cross product there, which would be an X with a vector after that. Those are three ways you can use that. Not the only three ways, but there's three ways you can use that. So now that I have that and I know how to do this, I can go ahead and work out the solution. So the solution is going to be, so this will also give us another opportunity for us to see how partial derivatives work, because you're not required to even have Calc 2 yet. I think you're supposed to be maybe or excuse me, maybe it's a co-requisite where you're supposed to be enrolled in it right now, but either way, it's not a big deal. The partial derivative with respect to x means pretend like any variable other than x is a constant. So you could literally take y and put parentheses around it and then erase the y and put a 4 in there, and then take z, put parentheses around it, erase the z and put a 7 in there. And long as you don't combine that 4 and that 7 to make it like 28 or something like that, then everything will work out. So let's go ahead and do this. I'm going to first say the x component of the force. So the x component of the force would be the negative partial with respect to x of u of x, y, z. So I'm going to calculate the partial derivative with respect to x of u of x, y, z. And that, of course, is equal to negative g m over, rather than write it with that square root, I'm going to say it's x squared plus y squared plus z squared to the 1/2 power, like that. And now I can go ahead and compute that. I'm going to say this is negative g m times the derivative with respect to x of x squared plus y squared plus z squared to the negative 1/2 power. Now, the derivative of something raised to the negative 1/2 power is negative 1/2 times the same thing, x squared plus y squared plus z squared, raised to the 1/2, -1/2 minus 1 power. So -1/2 minus 2/2 would be -3/2, like that. And now I have to take the derivative of what's inside the parentheses. And of course, the derivative of what's inside the parentheses is the derivative of x squared plus y squared plus z squared. But remember, we're taking the derivative with respect to x. So it's really x squared plus 4 squared plus 7 squared. Therefore, we only get 2x for that derivative. Okay. So now what you can see is I get a -1/2 times 2x. That's just going to be a negative x over the 3/2 power of x squared plus y squared plus z squared. So I can plug this back in above. The negatives will cancel each other out. I'm going to put a plus, and then I'm going to say this quantity is going to be x over x squared plus y squared plus z squared to the 3/2 power. So that's f sub x. Now I can do f sub y is equal to the negative partial with respect to y of u of x, y, z. And I can say the partial with respect to y of, now I'm going to go ahead and write it a little more conveniently, negative g m m times x squared plus y squared plus z squared to the -1/2 power is going to give me negative GMM. Oops, I lost that GMM up there a second ago. I should probably fix that. I will fix that in a second. So I do have the GMM here. Now I'm going to take the derivative of x squared plus y squared plus z squared to the -1/2 power. So that's -1/2 times x squared. So we're using the chain rule, remember, plus y squared plus z squared. Now that's going to be raised not to the -1/2 power, but to the -1/2 minus 1, which would be -1/2 minus 2/2, which would be -3/2 power. And now I've got to take the derivative of what's inside, and I'm taking that derivative with respect to y. So it's like 4 squared plus y squared plus 7 squared, and the derivative of that is just 2y. So I'm going to put the 2y here. Okay. Now let me fix this other line before I move on, because it's just a little bit of grouping stuff together. So what I'm going to do here is I'm going to expand this, and then I'm just going to take and put it equals right here and a negative g m m right there. Okay, so now I've got that. Now we can see that that thing that I was so excited about getting rid of all the negatives now reintroduces the negative, which means this guy is now going to be, and I'll go ahead and get rid of this one too, come think of it, is now going to be negative g m m x, like that. Okay, hopefully that's good enough. Now I'll continue with this derivative, and I'm going to get, again, the -1/2 is going to cancel out with the 2, leaving just the y, but I still get that negative up there. Oh, that's right. The negative with the other negative is going to cancel out. So this is going to give a positive g m m times y over x squared plus y squared plus z squared to the 3/2 power. So that means this is all going to be negative g m m y over x squared plus y squared plus z squared to the 3/2 power. And I think you can all tell what the z is going to be like. So there's probably not much need in me even showing it. So I'll go ahead and write out what the actual function the vector force field is. And what we see is everything will have a common factor of negative GMM. So and it's all going to have a common factor of this x squared plus y squared plus z squared. So I'm going to say negative GMM over x squared plus y squared plus z squared to the 3/2 power. And then all of this will be times x I hat plus y j hat plus z k hat. Notice that is a vector function. Notice it also looks a lot like the force of gravity. Remember, the force of gravity was F is equal to G M M over R squared. But if you wanted to make it a vector, let's imagine the actual mass. Let's say, imagine this big M is at 0, 0, 0, and this one's at X, Y, Z. If that's the case, then we want the vector to point towards the actual origin from that point X. So if we imagine a coordinate system, X, Y, Z, and we put a ginormous mass at the origin, and that mass is M, and then out here at this X, this Y value, and this Z value, we'd want that vector to point straight in from that point. And this point, of course, is X, Y, Z. If I wanted to make a vector from X, Y, Z to 0, 0, 0, the way I do that is I take 0 minus X, 0 minus Y, and 0 minus Z. And that's how you do it. In other words, you just literally take the final coordinate minus the initial coordinate and treat them like they're the individual numbers are actual vector components. So that they just add with positive, like positive and negative numbers do. So that vector points exactly the right way, points towards the origin. But if I wanted to make this vector into that, if I wanted to make the force GMM over R squared, that's the magnitude. If I want to make it a vector, I could multiply it by this vector, but then what would happen is the vector's magnitude would increase the magnitude of the force. So what I really want to do is multiply it by a unit vector. So this vector I might call negative R vector. What I want is negative R hat vector, which is defined to be R vector divided by the magnitude of R vector. I think you can all see that the magnitude of R vector is actually equal to the square root x squared plus y squared plus z squared. Does everybody see that? I still that negative out in front, by the way. Okay. So all I need to do is take this vector negative r, divide it by that square root, and that should give it to me. So now I can say, I'll do it in purple. So now f from this guy could equal g m m over, now I need the distance between the origin and the point XYZ. So that's going to be the square root x squared plus y squared plus z squared. But I got to square that. So I'll put a exponent of 2 there. And now I've got to multiply it by negative, I'll write it this way, negative x I hat minus y j hat minus z k hat. And then I've got to divide all that, of course, by the square root of x squared plus y squared plus z squared. So now I think you can see that what we really have is, and I'll write it in red here, negative GMM. Now notice I have x squared plus y squared plus z squared to the negative 2 halves times x squared plus y squared plus z squared to the negative 1 half. So that ultimately gives me to the negative 3 halves. So I'm now going to say x squared plus y squared plus z squared, 3 halves in the bottom. And now I'm going to multiply it by x I hat plus y j hat plus z k hat. And sure enough, that's exactly the vector that we got. Okay, y'all see that? Anybody have any questions on that one? Okay, so I realized the part where I took the the mass big M and put it at the origin, and then put the mass little m at the point x, y, z. I know that's some vector stuff that you hadn't seen before, but let me recap what I actually did so you'll know. In general, if you ever want a vector that goes from one point to another, what you're going to do is take the final point as if it's x comma y comma z in parentheses. That's how we do our ordered triplet for a three-dimensional point in space. So you do that final point, x, y, z, or call it x2, y2, z2, minus that initial point, x1, y1, z1, so that you end up getting x2 minus x1 is the x component, y2 minus y1 is the y component, and z2 minus z1 is the z component. In this case, however, the final position was literally 0, 0, 0. So it was 0 minus x, 0 minus y, 0 minus z. That's why I had negative xi hat, negative yj hat, negative zk hat. Now that gives me an actual vector that points from xyz towards the origin. That's exactly the way the gravitational force points for an object. Since we're treating it as a uniform sphere, the big M, as a uniform sphere at the origin, we already know that when something's spherically symmetric, it behaves as if all of its mass is right at the center. So it would pull directly towards the center of the sphere, which happens to be the origin. That's why we know that that's the direction it's going. So if we wanted to take the magnitude, which is given by Newton's law of gravity, g(m)m) over r squared, if we wanted to make that into a vector, all we have to do is multiply it by a unit vector. If I multiplied it by a vector that wasn't a unit vector, then I'd mess up the magnitude. So for instance, if I multiplied it by a vector whose magnitude was 2, then my force would now be 2 times too large. So it turns out, in addition to being able to subtract final coordinate minus initial coordinate to get the components of a vector, you can also make a unit vector by taking any particular vector and dividing it by its magnitude. Of course, dividing a vector might seem weird to you, but all that means is divide each component by that particular quantity. So what we really did was we divide the x component by the square root of x squared plus y squared plus z squared. We divide the y component by the same thing, and we divide the z component by the same thing. Or you can just write it like I did, where it's negative x I hat minus y j hat minus z k hat over the square root of x squared plus y squared plus z squared. So we can see that negative x I hat, negative y j hat, negative z k hat over the square root, that whole part is a unit vector. So let me remind everybody here. This is the unit vector negative r hat. Remember that hat on top of a vector means a unit vector, and r is generally just a vector that points radially outward. That's why I put a negative in front of it to show you it's this specific one that points towards the origin. Any questions on that? All right. So let's try another conservation of energy problem. But this time it actually is going to be, say, a conservation of energy. And I'm going to show you how, again, how to use the coordinates, or excuse me, the conservation of energy equation that I taught you guys. So what I'm going to do is I want to remind you what I taught you was work in plus potential energy initial plus kinetic energy initial is equal to work out plus potential energy final plus kinetic energy final plus E loss. Now, let me say a little bit about this first. For starters, work in is just a term that I happen to use because most of the problems I run into that aren't strict conservation of energy problems will say something along the lines of, if such and such a person applies a force of 100 newtons at 15 degrees to horizontal while pushing an object, 3 meters, that, that spells out to me work, 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 work. So I'm picturing that as someone adding energy to the system by doing work on the system. So I just called it work in, meaning work you're putting in. But to be honest with you, anything that you deem to be a way to put energy into the system, you should put on this left-hand side where it says work in. Okay, that means work in could have 4, 5, 6, 7, 8, 9, 10, could have 20, could have any number of work in terms. Okay, every type of source of energy that you're putting in should have, in some sense, a work in term for it. The main thing you want to do is make sure you count all the sources of energy put in and that you count them and use them exactly once, and that they all turn out to be positive and on the left-hand side. Okay, so if energy is going into the system, you want a term for each way that's happening, and you want it to be positive. Okay, on the right-hand side, I was basically used to either, something at the end of a conservation of energy problem, compressing a spring, or something at the end of a conservation of energy problem skidding to a stop, which I knew was a work being done against friction sort of thing. So I allowed 2 different terms in that case. Again, the work out could represent 20 different terms, and the E loss could represent 20 different terms or 5 terms or whatever. The main thing is, if you see any part of the system that's removing energy or anything that's removing energy from the system, you want to put them on the right-hand side and make them positive. There's only one thing that's supposed to be negative from what I told you, and that is when U is equal to negative GM over R. That's the only time you should have any of these things being negative. So let me reiterate by saying this. Each thing putting energy in the system should be put, on this side, and the energy should be positive. Okay. Anything taking energy out, or anything removing energy from the system, should be positive, and on this side. Okay. And then, like I said, that U is the only thing that's negative. All right, so that's the big rule again with this particular version. So I don't want you to get hung up on, well, what's work out versus what's E loss. It doesn't matter, just long as you account for everything that's stealing energy from the system, and you do it exactly one time, and you make sure it's positive and on the correct side, then everything will be fine. So in this problem, what we have is a rock. That purple rock there is 4 meters off the ground. And what we'd like to figure out is what's the velocity when that rock meets a height, or reaches a height of 1 meter above the ground instead of 4 meters. So the solution is going to go like this. So I'm going to start off with our equation, work in plus U initial plus K initial is equal to work out plus U final plus K final plus E loss. Okay. Now I am going on the assumption that I don't care about air resistance. It's going to be negligible. I don't care about friction, which obviously the rock's not touching anything, so friction shouldn't come into play. I'm not going to be compressing any springs. No one's going to give this rock a push. It's just going to be dropped such that the initial velocity is equal to 0. So with all of that in mind, I can say, well, work in is going to be 0 because there's nobody putting work into the system. Work out is going to be 0 because the rock isn't actually doing any work on compressing springs or pushing little kids on sleds. There's going to be no energy loss due to friction or air resistance, that kind of thing. Also, the initial kinetic energy, since the velocity is initially 0, the initial kinetic energy will be 0 as well. So you can see with this version of the conservation of energy equation, normally a buttload of terms is going to disappear from the get-go. Okay. So right now what I have is the mass of the rock times gravitational acceleration times 4.0 meters. That's the total potential energy. So I'll say, oops, I'm going to do it in a different color so we can see. So that's the term on the left. Now the term on the right is going to be mg 1.0 meters. And then that term right there, oops, I'm going to change colors again. That term right there is this term. And then I'm going to say plus 1/2 m v final squared like that. Okay. And I think you can tell that that term came from this one. Okay. Now, one thing you might be able to realize is right now there's an m in every term. So I could divide through by m, and in so doing, that gets rid of the m, which is good because I didn't give you the mass. And in fact, the book does a problem like this and doesn't give you the mass either. I'm going to go ahead and take this and multiply both sides of the equation by 2, because whatever you do to one side, you can do anything you want to an equation, but whatever you do to one side, you got to do to the other. So that's what I'm working out here. So what I get is 2g times 4.0 meters is equal to 2g times 1.0 meters plus v final squared. I think you can probably make this out and see that I've basically got vf squared is equal to 2g 4.0 meters minus 1.0 meters, like that. And I think you can see that this is in fact v squared is equal to v0 squared plus 2g x minus x0. Or in this case, you do it final because it's a minus, but still you get the same point here. You can see that conservation of energy techniques has just reproduced the kinematic equation. So that's kind of cool all by itself. So let's carry on. I'm gonna go back to purple. I don't know why I went to red and stuck with red, but I did. So here we are. So now I'm going to say v final is equal to the square root of 2 times 9.80 meters per second every second, which is the same thing as meters per second squared mathematically. 4 meters minus 1 meter is 3.0 meters, like that. So you see that I'm going to have meters squared per second squared under the square root. When I take the square root of that, that's going to give me meters per second. So I'll say 2 times 9.8 times 3. Now I'm going to take the square root of that. That's the square root of 58.8. So I get 7.67 meters per, whoa, nearly, meters per second as the final velocity here. Anybody have any questions on that one? All right, so that's really the ins and outs of using that equation, how you're going to use it. The rest of these should be fairly trivial. I've got another problem here just to show you another way or another thing that we can do. In this problem, we have a roller coaster. The roller coaster car is at the top of the leftmost hump, and that leftmost hump is 50 meters above the bottom of the trough. Okay.
Could you go back to the last slide for just 1 second?
Yes,
Thank you.
no problem.
All right, thank you.
No problem. All right, so we have it going here, and we're going to ask 2 questions. Question A is going to be, what is the V final at the bottom of the dip? Okay, I labeled it V final, and then I labeled the other one V final prime, just because it's going to be a different V final. For part B, what they want to know is at what height will V final prime, which equals 1/2 of V final, that's the whole question. So basically I'm saying at what height will the final velocity be 1/2 of the final velocity that you had at the bottom of the dip. Okay. So solution, I'm going to say work in plus U initial plus K initial equals work out plus U final plus K final plus E loss. We're going to assume that air resistance and friction are negligible. I'm going to assume that it started at rest. I'm going to assume that no work was put in during the time period that we're looking at this, and no work was taken out, no energy was lost, period. So with this case, at least with part A, what I'm going to do is say work in is 0, kinetic energy is 0, work out is 0, E loss is 0. And in fact, at least for part A, U final is going to be 0 because I'm going to choose to make this Y equals 0. So we already learned on that other problem that we're allowed to make the 0 of potential energy anywhere we want it. So I'm making use of that now. Okay. So now all I have to do is put in the information I have, which would be 1,000 kilograms times 9.80 meters per second times the height, which is 50.0 meters, is equal to 1/2 of 1,000 kilograms times V final squared. So you can see already that the 1,000 cancels out with the 1,000, and I get V final is going to be equal to the square root of 2 times 9.80 meters per second squared times 50.0 meters. Now you can really easily see that the units under the square root are meters squared per second squared. So I say 2 times 9.8 times 50. That gives me 980. And the square root of 980 should be 10 times the square root of 908 or 98. So that gives me 31.3. Now, technically speaking, you really had to do plus or minus here and plus or minus here. That's one of the downsides of conservation of energy methods. Sometimes you have to physically discern which direction a velocity will be going. So just keep that in mind, because you could actually choose a spot where the object's going up and call the velocity downward by mistake. So just keep that in mind. Now we'll do part B. Does anybody have any questions on part A? Okay, so I guess I'll go on to part B then. So for part B, what we want is the car to be up at that little purple arrow. Okay, we're still going to have sort of a lot of the same issues. So our work in plus U initial plus kinetic energy initial equals work out plus U final plus kinetic energy final plus E loss. So we're still starting with the potential energy, or excuse me, the kinetic energy equal to 0. I'm still assuming no work is put in or out, no energy is lost. Now, in this final thing, though, we're going to have some potential energy left and some kinetic energy left. So that's why I had to leave all three of those terms. Now I can write in 1,000. Oops, I don't want to write in red. Now I can write in 1,000 kilograms times 9.80 meters per second times 50.0 meters is equal to, and this is what we're looking for. We're actually looking for this height. So I'm going to do 1,000 decimal plate kilograms. 9.80 is decimal place. I don't know why I said decimal plate, but anyways, meters per second times y, and what I called this was y 1/2. So I'm going to call this y 1/2 here. And that's just the subscript to remind me, oh yeah, this is the height at which the vehicle reached half the velocity of above. So now I'm going to take this and say plus 1/2 of 1,000 kilograms. Now I'm going to take half of 31.3 and square that. Now, before I do all this, it'd be very smart for me to cancel out the 1,000 that happens everywhere and to multiply through by 2 both sides of the equation. Okay. So when I do that, I'm going to get 980 joules, because 2 times 50 is 100, and then 100 times 9.8 is 980 joules. That's equal to 2 times 9.8, that'd be 19.6 meters per second times y 1/2, which is what we're looking for. And then the 2, when it hits this 1/2 in the kinetic energy term, nothing happens. It just turns to 1. But in this case, I'm going to take 31.3 and divide it by 2. And then I'm going to square that. So it's 15.65 squared. And that's all I have left for that last term. So I'm going to call this 244.9. And that's 1 extra sig fig. And that's going to be meters squared per second squared, like that. So now all I have to do is solve for that 1/2. I'm going to say 980 minus 244.9 gives me 735.3, yeah, something like that. Yeah. .1 joules is equal to 19.6 meters per second times y 1/2. Now notice, oh, that wasn't joules when I wrote that 980 there. Sorry about that, everybody. That was meters squared per second squared. Let me fix that. Remember, it would have been joules if I hadn't canceled out the kilograms, but I had canceled out the kilograms. So the same thing happens here. This is going to be just meters squared per second squared. And that's 1 extra sig fig 2 there. So I'll underline that. Now I just take that 735 and divide it by 19.6. And that's going to give me 37.5 meters. So y 1/2 is equal to 37.5 meters. So what that means is when the object goes down a whole 50 meters, it reaches a speed of 31.3 meters per second. However, on its way back up, it gets a mere 12.5 meters from the top, and then is already or still 1/2 the velocity that it had. So that again just shows us that the velocity is not linearly related to the height, which you should realize just from setting conservation of energy equations, setting them up gives you potential energy, which is m times g times y usually. that can be set equal to 1/2 mv squared. So you see y is proportional to v squared, not y proportional to v. So that's why we don't expect that to occur at 25 meters instead of 37.5. Any questions on that one? All right. Well, we got about 20 minutes left, and I've now finished everything that I wanted to regarding chapter 8. So I'm going into chapter 9 now. So chapter 9 is about linear momentum. So let me start off by giving you some issues. So for starters, we started with Newton's second law of motion. So Newton's second law was said to be the sum of all the forces acting on a object or a system is equal to mass times dv dt, or mass times d2. Let's make this, to keep it consistent with vectors, I'll say r vector over dt squared, or m times a. Okay, now this one only works for m and constant forces. So if you have some scenario where you've put all the forces and the mass into F equals ma, and you find that solving for A gives you something where it's not a constant, then you know you shouldn't be using A. You should be using d2r over dt squared or dv dt. Okay, that's what makes it a differential equation as opposed to just a simple algebraic equation. But that was what we treated as Newton's second law, and it generally is sort of Newton's second law, but what Newton really said was this. Oops. Let's see. The summation of the forces is equal to the instantaneous rate of change of m times v. Okay, which, by the way, is defined to be dp dt, where p is defined to be mass times velocity, is a vector called linear momentum. Okay. Now that's for a single particle. For instance, you take the mass of the particle times its velocity vector, and that would give you the momentum of it. But we're going to slowly be migrating to solving problems of systems of equation, or excuse me, problems made up of objects that are systems of actual objects. So For instance, a baseball bat might be considered one object, or you might think of it as 10 to the 25th or 10 to the 26th individual atoms and molecules, right? So it can be that, but it can also be P for the system is equal to the summation from I equals 1 to N of M sub I V sub I, like that. So you could just add all of them up, and then you get another equation, the summation of the forces acting on the whole body is equal to d by dt of this quantity momentum. Okay, so this is actually the formal correct version of Newton's second law. It's F is equal to dp dt. There's some things you can get from that. So for instance, conclusions. For starters, the summation of the forces is equal to d by dt of mv, means the summation of the forces is equal to dm dt times v plus m dv dt. In this version, this is our rocket equation. And we call it that mainly because if you look at, for instance, our space shuttles, when we used to launch those, or just about anything, you'll see that most of the stuff we send to space usually has a huge gas tank. And that huge gas tank is blowing fuel out one end so that a huge amount of mass is being lost per unit time. And this accounts for mass loss. So mass lost / gained. But in terms of the rocket equation, the mass is lost. I just wanted to show that by using the quotient rule for derivatives, I was able to break dp dt into two terms. One term was the normal m dv dt that we've been using. The other term is what we were missing. Okay, so that's one of the conclusions that we have, is we really need to use that. I will tell you that I think the last section of your chapter 9 actually goes over using the rocket equation. And I want to say that there's one problem in the homeworks where they do it. Other than that one problem, I'm not going to ask you about it. So we're not doing anything. It's a little bit in the bushes, and we have to consider some masses and signs and velocities relative to the actual spaceship that's being fired, and so on and so forth. So it's a little bit complicated. So I choose to not cover that. If you actually are going into aeronautical engineering or something like that, you'll have ample opportunity to study the rocket equation and orbits and stuff like that. So I'll just tell you that I think, like I said, there's one problem where he sort of handholds and walks you through a rocket problem. That's fine. I don't mind you doing this for homework, but I'm not going to give you any question like that for the actual tests of any sort. Another conclusion we might find, though, is kind of neat. Before, the summation forces is equal to MA, implied the summation forces equals 0 gives us A is equal to 0, which implies what we called statics. So that's the first half of engineering mechanics, which a lot of books don't even, and courses don't even mention that anymore, unless you're actually, doing the hard work of reading the text in addition to doing the homework. Okay, but it's basically a 2-semester sequence, the first half of which is statics, the second half of which is dynamics. So that's what happens with the old version of F equals ma. If you consider the case of the net force being 0, you get statics, and that's how we can design, for instance, trusses for the roof of a house, or bridge trusses that holds up a bridge, a suspension bridge, and stuff like that. And that's the kind of neat stuff you can work. They have problems like that. I think they're in chapter 11, I want to say, in your textbook. You can do those. We skip that just because you're going to handle that in your engineering classes. But what I wanted to point out is, yeah, that is statics, but something interesting comes out from Newton's second law proper way. So the proper way, so proper Newton's second, the summation forces is equal to 0 implies dp dt is equal to 0. And that's, of course, a vector 0. Can anybody tell me what it means when a vector, or excuse me, when a derivative is equal to 0? Under what kind of conditions are a derivative equal to 0? What kind of functions?
Is that undefined?
That's the other version.
Extrema?
Yeah, that's the other version that you're thinking of. This is the one where if the derivative is 0, it means it has 0 slope, so it's a constant function. But good try. Thank you for putting it out there. What we find is P is equal to a constant. Okay. And what this is a new conservation law. It says basically, hey, the total momentum of the system is going to be a constant. Therefore, you can treat it like we did energy and say, whatever amount of momentum you had before some collision or something, you're going to have exactly that much momentum afterwards. So that's another big deal. I'm just going to write it like this. Conservation of linear momentum. So that's the conditions under which momentum is conserved, and that can come in handy. And in fact, there's a whole bunch of problems you can solve that way by using conservation of linear momentum. So we now know what the momentum is. We even know what the momentum is in the case of a system of particles. I will tell you that something else neat comes out of this. So we're going to ultimately be able to try to apply Newton's second laws, not to individual particles, but things like, let's say this thing. You know, this thing has little bits and pieces, but they're all made up of little atoms. And of course, atoms are really, really small. So small that we can sort of pretend they're smeared out over space, and we can treat them like continuous matter. And then that works out so that we can do things like calculate what's their reluctance to rotate. We know we had a reluctance to accelerate that was the mass of the object. Well, there should be something like mass that causes a reluctance to rotate, which is another form of acceleration. And in fact, that force type thing that makes things rotate is something we call, anybody know? The force type thing that forces things to rotate. Starts with a T. There's a wrench with that word in the name. A blank wrench. Nada? Nothing? I know infinity when I type it out. Like, oh Lord, don't make me type now. Okay, so yeah, it's torque. So there turns out to be another Newton's second law type thing for rotational motions, and it basically says the summation of all the torques instead of the summation of the force, excuse me, is equal to something like mass. It's called the moment of inertia, I, and then something like acceleration. It's called the angular acceleration, alpha. So that's a new equation we'll do. And in trying to understand how physical bodies move, we can say, well, maybe they're a rigid body. That'll make life a little simpler. So then we can assume that, you know, the distance between atom 1 and atom 2 is a constant. And then the distance between atom 2 and atom 3 is a constant, and keep on like that. That would make it a rigid body. That makes it a little easier to solve. But the main thing is we can use that kind of stuff. When we do, then we're going to reduce our physics problems down to a problem of how does the center of mass behave? Because, for instance, if I threw this pin, you know, it would spin and do all sorts of crazy stuff like that through the sky. But as I threw it, you know, some part of it, based on what we've been doing, should follow a parabolic path. Well, that parabolic path will be followed by something called the center of mass of the pin. And then all you need to make sense of a physical object like a pen is you need to know where the center of mass is, and then you can describe what the center of mass is going to do from your differential equations or whatever. And then you need a line that connects the center of mass to some particular atom or some particular spot on this object, and you can keep track of the angle of that particular line, and that will tell you how the whole thing behaves. So you'll know not only where the center of mass is, you also know where that end of the pencil is. Okay, so that's ultimately what we're shooting for. And it turns out when we do that, we introduce a new concept called the center of mass, and that center of mass allows us yet another way to solve physics problems. That pretty much every problem we can solve with conservation of momentum, we can also solve with center of mass. So let me take for a second and just talk about the center of mass for you. So for instance, if you imagine a chunk of wood that we've cut into a meter stick, something like this, okay? Now, if this meter stick is made of uniform wood, then the center of mass will be in the plane that I'm able to hold my finger out and lay the meter stick on. So for instance, if this was to represent our meter stick and I tried to balance this on my finger like that, then this plane that my finger is in, this vertical plane, that is where the center of mass is, clearly, because the center of mass has to be suspended above something, because an object behaves as if all its mass is at the center of mass, and therefore you have to have the center of mass held up or it'll accelerate towards the ground. So in this case, we would say the center of mass, if it's uniform, the center of mass is equal to the 50.0 centimeter mark. Okay, and let's say its mass is equal to 1.00 kilograms. Okay, now let's say instead of a meter stick, I'm going to say we have something like a meter stick, but it's a meter stick that's combined with some other stuff. Well, no, I didn't want to do that. Well, that did not work well. Okay, so this is like our uniform meter stick, and I'm going to do something crazy. I'm going to put the origin of the coordinate system right here. So that's my y-axis, and this is my x-axis. And now at the 5 centimeter mark, I'm going to put a mass, m equals 10.0 kilograms right there. And make it be more or less glued to the meter stick. And what we'd like to know is, well, what is the new center of mass? Well, it's sort of like taking an average. So I will tell you, and I'm sort of arguing this formula out right now, and then you're going to be able to use it. But the x center of mass, if you think, okay, well, that 10 kilograms is 5 centimeters away, so that's tending to rotate it downward. Let's go ahead and take into account both of those. Then I'd say 5 centimeters times 10 kilograms plus Now remember the meter stick was uniform, so that's 50 centimeters times 1.0 kilograms. That gives me the total pull that it has down and to the right, okay? But if I were to take that and divide it by the total mass, then that would sort of give me the average position, because I'm getting rid of the mass by dividing it out. So I'm really just getting a position. And of course, the total mass is 10 kilograms plus 1 kilogram, which is, notice 5 times 10 is 50, and 50 times 1 is 50. So 50 plus 50 is 100. And then if I divide 100 by 11, I end up getting 9.09 centimeters. That's the center of mass, and that's the way you're going to calculate it. As you can tell, it'd probably be a Y center of mass, would be the same formula. In fact, I'll go ahead and write it. I'm going to say the X center of mass is equal to X1 M1 plus X2 M2 plus dot 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 on up to plus XN MN. And then I've got to divide all that by M1 plus M2 plus dot 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 plus M sub N, like that. So that's our general formula for the center of mass of any number of discrete objects. You can see that a Y center of mass would be a similar formula: Y1 M1 plus Y2 M2 plus dot 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 over dot dot dot. You can see how that works. But what if it wasn't discrete? Well, then we're going to pretend it's going to be continuous, even though atoms exist. And in that case, we'd say X center of mass would be the integral of X dm over the integral of dm, where dm is going to be equal to either a linear density, lambda times dl, or a area density, which would be sigma times dA for area, or a normal density, rho, times dV. Okay, this is something that's not going to go away. That lambda, that sigma, that rho, you're going to be using it for the center of mass. You're going to be using it for the moment of inertia. Then when we get into next semester, we're going to be using it for charge distributions and current distributions and all sorts of stuff. So you need to have some idea what it is. But basically, if something's like a bicycle spoke, that's essentially like a one-dimensional object. So you don't need to waste much time measuring diameter in two different directions. You really only care about the length. And if you took, say, 1 millimeter of length of it and divided the mass of that one little millimeter of length by that 1 milliliter, you'd get the density lambda. If you had a flat plate, literally like a sign, like a traffic sign or something like that, you know, the dimensions of the height and width are huge, but the thickness is thin. In that case, it's not reasonable to waste any time measuring the thickness. You just measure the width and the height, and then divide that mass of that width and height sample by that area, and that would give you the area density, which is sigma. And then, of course, if you had a three-dimensional object, you'd use rho. If they were uniformly distributed, what that would mean is lambda would be a constant in units of like kilograms per meter. Sigma would be a constant in units like kilograms per square meter, and rho would be kilograms per cubic meter. All right. Now, I haven't really worked any problems with this. The main thing is I just wanted to expose you to it so we can jump right in chapter 9 next time and do some real linear momentum stuff. You guys are free to go. I'll wait for the last person to leave in case anybody has any questions. Other than that, thank you for coming, and I see you folks later.